So this is going to be the first two chapters of the probability section, which is section 4 of Stats book. This is just going to be basic probability introduction. A lot of this you might already know, but there's going to be a few new terms, terminologies, and investigations that you might not have been aware of before. So it's going to be a little bit of review and a little bit of new stuff. So first off, what is probability? So probability is kind of the core of inferential statistics. Remember, inferential statistics is using data to kind of predict or guide policy making or future events. And again, a lot of that deals with probability about the chance of something happening. Because if something's likely to happen, you want to make sure you're adequately prepared to react to it. Um, so for any event, your probability is always going to be between 0 and 1. So an event is, again, an occurrence of something. And the chance of it happening is always between 0 and 1. So you can't have a 125% probability. You can't have a negative 6% probability. And usually, again, probability for us is going to be given as a decimal. So rather than saying 50%, we'd say 0.5. Rather than saying 75%, we'd say 0.75. It's the exact same thing. It's just that since it's a decimal form, you can usually calculate with it at a much quicker pace because usually you don't want to use percents in calculations. You want to use the decimal form in calculations. So we just kind of keep it as decimal throughout the entire thing. So 1 here actually represents 100%, and 0 here represents 0%. So that's why it's between 0 and 1, not 0 and 100, because we're talking about the decimal form of the answer. And there's actually two different, I wouldn't say schools of thought, but there's two different kind of branches of general probability that we're going to get into. So how is this process breaking down? So there's a few terminologies we need to go over real quick. So an event is simply a collection of results from a procedure. So it's what could happen. So an event is what could possibly happen. Think about it that way. A simple event is an event that does not have any extra pieces, I guess would be the best way to describe it. So for example, rolling a die would be a simple event because when you roll a die, you have 1 through 6 as the possible outcomes, assuming it's a standard die. So that's it. It's a simple event. You can't break that down any further. Whereas, say, getting an A on a test, that is definitely not a simple event because there's a lot of factors that go into that. You have study time, you have class attendance, you have ease of topic. So a simple event is an event that basically has one driving factor, whereas a compound event is an event that has multiple driving factors to it. Again, something like that would be also the chance of flipping heads and rolling a 6. So what are the probability that if you have a die and a coin that you roll a 6 and flip a heads? That would be a very easy compound example procedure because you have two events, flipping a heads and rolling a 6. Two events in one single compound event, and then that single compound event can be broken down into rolling a die, a simple event, flipping a coin, simple event. So simple events together make compound events. Just like, again, numbers, when you put them together, make bigger numbers. The sample space is basically all the possible simple events that an outcome can have. So for example, flipping a coin would be all the possible outcomes for that simple event. So flipping a coin has two outcomes, heads and tails. That's the sample space. So it's all the possible outcomes for a simple event that, again, that can possibly happen. So how do we notate this? So P, capital P stands for probability, obviously. And so this is read as P of A, the probability of event A. So usually we designate events as A, B, and C. And again, usually this is all with capital letters, although I won't count you off if you do lowercase letters. It's just that conventionally probability stuff is done with capital letters. Make sure I do a mic check here because it might cut out on me because I don't have my background there. So what's the first type of probability we're going to look into? And that's experimental probability. So by its name, experimental probability is basically the probability that results from conducting an experiment over and over and over and over and over again. So the way you get that is if you want to figure out the probability of event A happening from an experiment, you take the number of times it has occurred so far divided by the number of trials you've conducted, and that will give you the probability of event A occurring in the next trial. So let's take, again, rolling a die as an example because that's kind of a universal thing. If you roll a die, what's the probability you get a 6? Well, we know that theoretically, but experimentally what you have to do is if you want to know the probability of rolling a 6, you would have to roll a die 100 times and then count the number of times you get a 6. So let's say you roll it 100 times and you get a 6 29 times. Well, then your probability is 29 sixes out of 100 throws, which is not 1/4. That was a mistype on my part there, but that would be 29%. So your experimental probability would be 29%. Now, is that accurate? Well, depends on how many experiments you run. The more experiments you run, the closer to the actual probability you get. Because as we know, if you want a 6, it's actually a 1 in 6 chance of getting a 6 when rolling a standard fair die. But that's the thing about experimental probability is only as good as the number of trials you run. If you only run an experiment 5 times, it's not going to be a very good accurate representation. Because theoretically, for example, if I flip a coin and I get a head twice, then my experimental probability of getting a heads is 2 out of 2, when we know that's not true. So again, experimental probability is simply the number of times something has happened divided by the number of tries you did, and that result is your experimental probability of that event happening in the next trial. And again, this is changing over time. So every time you run a new trial, your experimental probability changes a little bit and hopefully gets a little bit more and more accurate. So the theoretical one is probably the one that we're most familiar with. So the second type is theoretical probability, and that's simply they call it the classical approach, but it's simply taking the number of events that can happen and working those numbers to get your probability. So the way you get the probability of A happening is you take the number of ways A could possibly happen divided by the number of possible events that are entirely possible, not to be redundant there, and that division is your probability. This is usually abbreviated as S over N, whereas S stands for the number of ways the event can happen, and N stands for the number of events in all that can happen. So if we go back to our die example, to do this theoretically, we would say the number of ways we can roll a 6 on a die is 1. There's one side that has 6 on it on a standard die. The number of things that can happen when we roll a die is 6. I can roll a 1, a 2, a 3, a 4, a 5, or a 6. So there's 6 things that can happen when I roll a die. There's one thing that I want, which is rolling a 6. So my probability of rolling a 6 is 1 out of 6, theoretically speaking. So again, this is probability of using the events that are given to you rather than experiments or trials. To put another way, what if I wanted the probability of rolling a 1, so I'll put rolling here, rolling a 1 or 2. Well, how many ways could I roll a 1 or 2 on a die? Well, I can roll a 1 or I can roll a 2. So there's 2 ways I can roll a 1 or a 2. And there's 6 things that can possibly happen. I can roll a 1, 2, 3, 4, 5, or 6. So 2 ways I want out of 6 ways total, which gives me a probability of 1/3 or 0.3 repeating, or 33%, 33.3%. So theoretical is the way that you probably were first taught about probability, and again, that's why they call it kind of the classical approach. But again, it's kind of the same thing as experimental, just with a different focus. So based on the theoretical system, if let's say a 65% is passing, so if we say 65% is passing and you can score anywhere between 0 and 100%, let's say there's no extra credit, then that means the chance that you pass an exam is 35%. Because if you score between 0 and 35%, you fail. And if you score between 36 and 100%, you pass. So there's a 35% chance that you, I shouldn't say passing, actually, shouldn't it be? There's a 35% chance that you fail the exam, right? Because 35% represents the failure. So let me say fail, because 0 through 35 is a failing grade. But again, as we know, that's not quite true, right? And I should say, oh wait, no, I did have that right. My bad. I'm a little bit off today. Sorry. Usually I'd restart the video, but I don't feel like it. So if we say that 100 to 65, line there, 165 is passing, and 64 to 0 is failing, that means you have a 35% chance of passing. So I did have it right. It shows me second guessing myself. So it's a 35% chance of passing exam, because if you score between 0 and 65, you pass. If you score between 64 and 0, then you fail. But again, this is not necessarily an accurate representation, right? Because there are more factors in you passing the exam. You're not as equally likely to get each percentage. The chance that you get a 0% on an exam is far, far, far less the chance of you getting 100%. Because the chances are, assuming that the exam has a sizable amount of questions, that you're going to at least get one right. So since this is not an even split in the sense that getting a 0% is not the same chance as getting a 1, a 2, a 3, a 4, a 5, all the way up to 100, and because you have some control over that, like you could study harder, you can attend class more attentively, that sort of thing. So this is not necessarily a accurate representation of the situation you're in when you're taking an exam if 65% is a passing mark. So again, just be careful of these things that sound like they're correct on the face, but with a little bit of thought, they're not. It's like saying the chance of you winning any sporting game is 50-50. Well, again, just depends on how hard you play, how you feel that day, what the weather is, that sort of thing. So theoretical is nice, and that's the reason that they teach it to you first in your schooling is that they first introduce probability as a theoretical concept there. But it's often not useful when you have a very complex situations, like for example, car crashes. If an insurance agency wants to analyze what's the likelihood of an average teenage driver getting into a car crash, you can't really do that theoretically because there's no way to get kind of a sample space that's easily useful for that. So you have to run it by an experiment. What you do is you have to look at past car crashes, figure out how many of them involve teens, how many of them total in a year or something like that, and then get those and divide them out and get your experimental probability that way. Or again, you can run a simulation. So if you want to figure out, okay, what's the chance that a teenager gets to a car crash, you can analyze the factors, maybe set up a computer system or simulation that kind of simulates a teenage driver driving down a 1 mile stretch of road on normal everyday traffic conditions, and it can run a trial over and over and over again to see how many times that car crash happens, and then you can use that data to guide your policy making. So if you can create a simulation or sort of a fake little world here that you can test something out in, then you can get experimental probability that way, and that's often better for more complex scenarios that don't have a clear-cut sample space like rolling a die does. So the other thing about especially experimental is again this law of large numbers. So the more trials you measure, the better your experimental probability is going to be, and the better your probability is going to be in general. So again, if you survey 10 people, that's going to be a lot less accurate, or your data is going to be a lot less telling than if you survey 10,000 people. Or again, if you take an athlete like Reggie Miller and you figure, okay, what's the chance that he gets a free throw? Well, if you use one game as your approximation, and he makes 50% of his free throws in that one game, so he makes half and he misses half of his free throws, well then his probability of getting a free throw is 50%. But is that accurate? Well, no, because you're just using one game as your sample space. What would be better is if you used his entire career. So if you take his entire career and my mic cut out there, my bad. So hopefully I'm back here. Let me check. Uh, yes, okay. So if you take the entire event, or not the entire, you take his entire career and you figure out the chance of him making free throws throughout all his career, that would be a better approximation of his free throw percentage. So again, key concept here to hammer home is that the more samples and surveys you do, the better your results are going to be. Come on, there we go. So how do we actually work some of these problems here? So generally, we want to round our answer to 3 decimal places unless otherwise specified. That's usually how probability is given. And most often, if we have an easy going event, we can actually just model the sample space and go off that. So for example, let's say we want to find the probability that a couple having 3 children will have exactly 2 boys. So if I want exactly 2 boys, well, what are all the possible scenarios for having 3 children? Well, you can have all three be boys. You can have two be boys and one be girl. You can have the first and the last be boys and the middle be a girl. You can have the first one be a girl and the last two be boys. So you basically model the entire possible sample space out. It takes a little bit of time and takes a little bit of thinking, but it's not that difficult. And then you look here and say, okay, if I want exactly 2 boys, how many of these situations have exactly 2 boys? Well, we have one, two, three. So there's 3 situations where I have exactly 2 boys out of 1, 2, 3, 4, 5, 6, 7, 8. Out of 8 situations. So the chance that I get exactly 2 boys is 3 out of 8, which if you divide that out, ends up being 0.375. So that's kind of the general way we start working out problems is if we can, we just simply model out the sample space, so all the possible outcomes in one spot, and then just figure out how many of those possible outcomes do we want. And in this case, it was the outcomes that have exactly 2 boys. So that's what I just did there. I'm not sure why I had that pop up. So the first thing we need to do though is be aware of small differences in how the problems are stated. So if you look at these two here, bring that up there. So let's say I want the chance that a couple having 3 children will have at least 2 boys. Not exactly, but at least 2 boys. So at least means I want 2 boys or 3 boys. At least means this or more, right? So if I want 2 or 3 boys, I'm first going to model out the situation like I did here, write out all 8 possible outcomes. If I want at least 2 boys, that means I want, let's say, 1, 2, 3. Those have exactly 2 boys. And then this one also has at least 2 boys. It has 3, but 3 is at least 2, right? So all 4 of these possibilities are going to be part of my target outcomes there, right? So I have the target outcomes, 4 on top, over the total possible outcomes, which is 8 on bottom, which gives me a probability of 50%. So the probability that this couple will have at least 2 boys is a 50% probability because 4 out of the 8 possible outcomes have at least 2. Now, if I tweak just one word here and say, what's the chance that they have no more than 2 boys? Okay, so no more is different. No more is actually the exact opposite. No more means I want 2 or 1 or 0. So I basically want 2 or less. So if I look back up here, how many of these cases have at no more than 2 boys or 2 or less boys? So I'm still working with these 3 here. 1, 2, 3. This one also has no more than 2 boys. This one has no more than 2 boys. This one has no more than 2 boys. And this one has no more than 2 boys. So all 7 of these possible outcomes fit in that sample space. So I have 7 cases where there's no more than 2 boys. I have 8 cases total. So 7 out of 8, or whatever that decimal is, would be my probability there. So pay very careful attention to the wording in these types of problems so you know exactly what type of outcomes you're going to want to look at. So one thing that's going to come into play, especially later on, is the complement. So the complement of an event is basically the probability that it doesn't happen. And it's usually denoted by this little bar on top of the variable. So the probability of A, and this is the probability of the complement of A. So this right here is the probability that A does not happen. And the thing about complements is that they make a one-to-one connection with their normal probability. So the chance that A happens plus the chance that A doesn't happen is equal to 1. I mean, that's just, again, the event is either going to happen or not. So if I take all the cases where it happens plus all the cases where it doesn't happen, I get a 100% chance. One of those two things will happen. And this is a rule that we're going to fall back to quite often to solve more complex issues. Now, again, normally I would do this, but I don't have a class with me in front of me, so I can't really do that question. But let me show you another example here. So let's go back to the boy-girl example. So if we have, again, a couple that has 3 kids, and if I want the probability of at least 1 boy. So remember, 1 is equal to, in this case, the probability, if I want the probability of at least 1 boy, this is the probability of at least one boy, right? Plus all the other probabilities is equal to 1. So if I take all the probabilities where there's at least 1 boy, and what's the opposite? Well, at least 1 means 1 or more. So if I add that, let me give myself some space here. Take the probability of at least 1 boy plus the probability of less than 1 boy, that will equal 1. Because these are all the cases where there's 1 or more boys. These are all the cases where there's less than 1 boy. And that has to add up to 100% because one of those two things will happen. They're either going to have 1, 2, or 3 boys, or they're going to have no boys. There's no other outcome for that. So all we do to figure out the probability of at least 1 boy is we simply subtract this probability from both sides, and we end up with this equation here. The probability of at least 1 boy is equal to every possible combination in all, which is 100%, minus all the ones you don't want. So think about this trick as taking everything that could possibly happen minus all the cases that you don't want to have happen. And if you take out all the cases you don't want to have happen, you're left with what you do want. So this would be 1 minus, what are all the cases where there's less than 1 boy? So that would just be this one right here, right? This one has less than 1 boy, aka 0 boys, right? So this is 1 out of 8, which gives us a probability of 7 out of 8. And again, we can check that by counting them up. So if I want the probability of at least 1 boy, well, there's 1, 2, 3, 4, 5, 6, 7. Now again, that would probably be an easier way of doing it, but I wanted to show this procedure here because it's more useful in more complex situations that we're going to encounter later on. So I want to start off with sort of an easier example to show the logic behind it. And again, we can do this for at least and at most cases. So if I want the probability of less than 2 boys, I should probably use at most there. So if I want the probability of, let me change this out here actually. Let's say, because I want to use the word at most, because that's in the topic there. So if I want the probability of at most 2 boys. So at most means I want 2 or 1 or 0. So at most is kind of like no more than. You cannot go above this number. So the probability of at most 2 boys, so probability of at most 2 boys is going to be equal to everything that can happen minus, well, if at most means 2, 1, or 0, that means this is the probability of 3 boys. I should say 3 or more, but again, if we're only having 3 children, we can't have more than 3 boys. So if I take all the cases that can happen and I subtract off all the cases where there's 3 or more boys, I can get the probability of having at most 2 boys. So the probability where there's 3 boys, well, that's only this one right here, which is again 1 out of 8. So there's a 1 in 8 chance that they have 3 boys. 1 minus that means there's a 7 in 8 chance of them having at most 2 boys. Because again, actually it's the same probability of having at least 1. But again, this concept here is I take everything that can possibly happen, represented by the 1 here, 100%, and I subtract off all the probabilities that I don't want. I don't want the probability of having 3 boys. I just want to have the probability of 2 or less, aka at most 2. So this is, again, this doesn't really come to play a lot now because the samples we're going to be dealing with are a little bit easy to represent in terms of sample space. But this is a very major sort of idea that we'll come back to later on, but I want to introduce it here just to make sure that we have some introduction to it. So the last thing we'll talk about here is odds. So odds are not the same as probability, although people often use them interchangeably. The odds is actually a comparison of probabilities. One way to think about it is that the odds is simply the number of ways things can happen compared to the number of ways things cannot happen. Whereas probability is the number of ways things can happen compared to the total number of possible events in all. So odds are simply caring about things that happen versus things that don't, whereas probability cares about things that happen compared to everything that could possibly happen in a given situation. So a slight difference, but a key one. So there are actually 3 kinds of odds: odds against, odds in favor, and the payoff odds. So odds against is simply the chance that something does not happen divided by the chance that something does happen. Again, that's what I was saying before here. Odds against meaning not for. So the way you get it is you take the chance that something does not happen divided by the chance that something does happen, not by the total possibilities like a probability, but the chance, the actual probability that something does happen, and then that result, usually represented as a fraction, is your odds against. Or again, another way you can think about this is simply the odds against is the number of things that cannot, or the number of ways things cannot go your way compared to the number of ways things can go your way. So I want, let's say, the odds against, I can't spell for some reason. Let me erase that here. My mic might be cutting out here shortly too. So try this again. See if I can't spell it right. Odds against, there we go. Odds against rolling a 6. So the odds against rolling a 6. Well, there are 5 ways I cannot roll a 6. 1, 2, 3, 4, 5. Compared to 1 way that I can. I probably put this as a fraction. So the odds against rolling a 6 is 5 to 1. Because there's 5 ways I cannot roll a 6 compared to 1 way that I can. So that is how you would get the odds against rolling a 6. If I want to, I can make this in terms of the probability version. So the probability of not rolling a 6 is 5 out of 6. The probability of rolling a 6 is a 1 out of 6. But what essentially happens here is that these two 6's cancel out, and I'm just left with 5 over 1. So if you want to do it as the probabilities, you can, but the bottoms are going to cancel out anyway, and they're going to be the same. So it's really just the number of ways things cannot happen divided by the number of ways things can happen. So if I want the odds against something, how many ways can it not happen? How many ways can it happen? Compare those two numbers in a fraction. Again, usually this is written as a fraction, not as a decimal like probability. The odds in favor is just the flip version. So the odds in favor are the chances that something can happen compared to the chance that something cannot happen. So the odds in favor, so in favor of rolling a 6 would be 1 to 5, not 1 to 6. Again, people often freak out about this. 1 to 6 is going to be the odds of, or the chance, the probability of rolling a 6. The odds in favor of rolling a 6 are 1 to 5. One way I can roll a 6, 5 ways that I cannot. So the odds in favor are ways I want divided by ways I don't want. Not probability. Again, not probability. The payoff odds are the weird ones. The payoff odds represent the profit you make off of a bet compared to the amount you have to bet. So this is often set by the casino or whatever you're playing your games at, and we'll go over an example about how to look at this one here. But this one's a little bit stranger than the odds against and the odds in favor. So let me do an example with this one rather than trying to explain it theoretically here. So let's say you bet $5 that the ace of diamonds will be the top card of a deck. If you don't know, the wake up of a deck is that there's 4 types of suits. So there's a diamond, there's a heart, there's a club. You can look at my artistic skills here, and there's a spade. So there are 4 types of cards, and each card has the same amount of values. So there are an ace, a king, a queen, dot 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 of diamonds, ace, king, queen, dot 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 of hearts, clubs, and spades. So each type of card has 4 versions of it. So the ace of diamonds is one version of the ace. And then there's an ace of hearts, there's an ace of clubs, and there's an ace of spades, just in case people don't know the makeup of a deck here. So the chance that you get an ace of diamonds is 1 out of 52. There's 52 cards in a deck. There's 1 ace of diamonds in that deck. So the chance of getting the ace of diamonds on the top is 1 in 52 chance. Again, this is probability here, this 1 in 52. One way I can get an ace of diamonds, 52 ways possible that something can happen. There's 52 cards possible I can pick. One of them is the ace of diamonds. And let's say the game is set so the payoff odds are 25 to 1. So the person playing the game sets them as 25 to 1. What are the odds against? So the odds against, again, is the number of ways this can not happen compared to the number of ways it can happen. So if I want the ace of diamonds, well, there's 51 cards that are not the ace of diamonds, and there's 1 card that is. So the odds against are 51 to 1. 51 ways this cannot go your way, divided by 1 way that it can. Again, I go through the probability version here if you want to look at that, but really all it comes down to is number of cards that are not the ace of diamonds compared to the number of cards that are the ace of diamonds. So the odds against are 51 to 1. The odds in favor then would be the reverse, which is 1 to 51. So the odds in favor of getting the ace of diamonds is 1 to 51. The odds against is 51 to 1. Now, what would be the net profit you'd make if you win? So if this is the payoff odds, 25 to 1, what this means is that for every $1 you bet, you get $25 if you win. Or again, net profit compared to the amount bet. So if you bet $1, you can earn 25. So that means that if you bet $5, which is what they say here, you bet $5, that means you're earning, so let's see here, it's 25 to 1, right? So if I bet $5, then I times this side by 5, I'm going to earn $125 if I win. So if I bet every $1, I get 25 back if I win. So if I bet $5, I'm going to do that 5 times, so I get $125 back. So that's how you kind of read the payoff odds there. Is the payoff odds tell you how much money you get per how much you bet. So if this was 25 to 2, that means for every $2 I bet, I get $25. If this was for some reason, and this is sometimes if you're betting on like a boxing match or something, it'll happen like this. If my payoff odds were say 2 to 5, that means that for every $5 I bet, I get $2 back. So if I bet $5 and win, I get my $5 back plus 2 more dollars. So this 25 here, this 25 does not include that $1 that you spent. You get that dollar back, and then you get 25 more on top of it. So this does not mean you're losing money if this is your payoff odds. This means that you have to bet $5 in order to earn 2. again, if you're betting on like a boxing match or a martial arts match, oftentimes if the person is favored to win, so if you're betting on somebody who people expect to win, this will be kind of what the payoff odds would be. You have to bet more money to get a little bit back because you're betting in favor. You're betting with the person that's expected to win. So if you bet $5, you're only gonna get two back. Whereas if you bet on somebody who has a little bit less chance of winning, then usually their payoff odds are more like this one, where you bet a smaller amount and you get a larger amount back if you win, because again, you're playing against the odds essentially. So if you're playing for fun and not for profit, then the payoff odds would be the same as the actual odds against. So that if the payoff odds are equal to the odds against, that means in the long run, you end up with a net loss and a net gain of zero. Because the odds that something does not happen matches or is represented by the amount of money you get for taking that risk. Now, oftentimes casinos will figure this out and then make sure they don't do that because casinos exist to make money, right? So they want to make sure that they're adjusting their payoff odds so that over the long run, people are losing money on average than gaining money or coming out even. Because if people just break even, then the casino doesn't earn any money, except maybe off drinks that they're ordering or something. So the casino makes sure to manipulate the odds of each of their games so that the payoff odds are always in their favor, essentially, that they're always getting money from people in the long run. So that's the end of that one. Again, lots of information I know. Hopefully the first part of it was kind of a review about the basics of probability. The last part about odds and complements and stuff like that, that might have been new for you. So once again, please let me know if you have any questions. This entire chapter here is about probability, so it's very kind of formulaic and stuff, a little bit different than the past ones. So if you have any questions, let me know. Otherwise, hopefully this helped you out. Have a good day.